on this. Okay. It's one of my favorite cartoon series. Oh, excellent. All right. So, so for due this week, we're supposed to have chapters 3 and 4 homework due this week. Because we're just starting chapter 4 today, I'm going to move that homework, chapter 4 homework is going to be due at the beginning of next week. In fact, it'll be due on Wednesday, the 16th. So I'm going to move that. So don't worry about that. There is on Canvas a thing called the tentative schedule for lectures and homework due. And it also has our tentative first exam, which is scheduled for September 30th. Okay. Now, that means that the week of September 21st, we're going to have 3 days where we can come in and take mock exams. It'll be a 5 questions, and what it's basically going to do, it doesn't count for points or anything. It's so that to make sure your computer has everything you need and you get used to logging in, doing the ID validation, and doing the and having it see that you have enough processor power. In addition to that, I'll send out instructions. There are certain instructions they recommend. For example, it's best to turn off all your other programs and reboot your computer right before, because that'll take some bandwidth hogs out of your back-end daemons. And so it'll allow it to really run more efficiently and have you have a much less stressful testing experience. So starting next week, actually the week of the 21st, which is 2 weeks from now, we'll do 3 mock exams. And so that'll just, if you log in the first time and everything works, go ahead and just log in the second time just to make sure. If everything doesn't work, go ahead and contact Top Hat. Top Hat support's been pretty good. They've gotten all my other students in very quickly, so I think they can handle it. And so then that way you'll have a couple of tries after getting help to make sure that you're good. And if you still can't get it working, I have a workaround for that, and we'll talk about that as that time progresses. But keep that in your head. We have that exam coming up on the 30th of September, and it will be covering chapters 1 through 6. Okay, the next thing is homework has been changed because of the timeline. Where is my other document? Due this week. And let's see, there is, yes, all right, so that's all good. Update on the lab. You should be receiving an email tomorrow and or Friday specific to your section. There's an online section and there's a live section. The live sections will be split into A and B. You'll get when you need to come and the schedule according to the labs that you will actually be doing. So for A-B students that are live, they're you'll start alternating next week. A's go first and then B's go the following week, except for the last day checkout day. It's a small enough section that all you're doing is checking out. So we'll have the first group come for an hour and then the second group come, and we'll all close out at the same time. But if in your off week, you'll be doing the exercise that the online lab will be doing. And so we'll have something to do every week and give us that lab experience. Okay, so there'll be another email about that tomorrow and Friday. So look for that. Okay, so that's all that's due this week, and that's our target. Our target this week is to get through chapter 4 and maybe start chapter 5. But we're going to do chapter 4 today, and we're going to get moving along with it. Okay. So I hope you all had a safe Labor Day holiday. I put the labor in Labor Day by working in my garden, and I almost threw my back out, but I didn't, so yay. Okay. So that being said, just to remind you where we were talking on the last lecture about alkanes and about what they are and what hydrocarbons are and the different classifications of hydrocarbons. Today, we're going to start with the new thing, the chapter 4, which is the alkenes and alkynes. Okay, and I am presenting my top 4 goals of the chapter 4. Now, there are full slides and videos as well as and the reading assignment in the book that add additional information to these goals, but these goals are the big important things that we need to get our heads around. So the first thing I'm going to do here is I'm going to share my screen. Let's see how that comes along. And got my thing up here. All right, okay. So you should see my slides up there now. And so let's go ahead and continue with chapter 4, alkenes and alkynes. So up to now, we were talking about carbon-carbon single bonds and the idea that the carbons and hydrogen is what made them hydrocarbons. So our first goal is to look at the difference between our hydrocarbons and the alkenes and alkanes because of the use of both sigma bonds, which is a direct bond, and the pi bond, which is an overlapping bond, and the hybridization required to do this, okay? So if you'll remember, this diagram we used when we filled our energy levels in chapter 1. We started filling from the bottom up, and when we got to carbon in that energy level 2, we had a total of 4 valence electrons. And we figured out it was easier to hybridize, spread those 4 valence electrons in between those 4 possible orbitals by sharing that energy. And that first kind of hybridization is what we called sp3 hybridization, because it used the s orbital and all 3 p orbitals. When we do that, we can form that tetrahedral structure, and we have 4 bonds to carbon because we have those 4 electrons, 1 in each of these orbitals, and it makes 4 equal bonds, okay? Now, the next level of hybridization is, well, we don't have to share all of the p's. If we only share 2 of the p's, we get 3 equal orbitals, and that's how we get to that that trigonal planar structure. We have 3 equal orbitals that do that sigma bond, and we have 1 p orbital left over. That p orbital is the one that can do that secondary type of bonding, that pi bonding. That bond is above and below the sigma bond, and we'll look into that a little bit. Now, you can also just share 1 of the p's and get 2 bonds that are sigmas that are 180 degrees apart, and that leaves us 2 pi p orbitals to do 2 different pi bonds, okay? So the hybridization of the carbon leads to the kinds of bonds it can do and the number of bonds it can do. sp3 only does sigma bonds, and it makes 4 sigma bonds. sp2 does 3 sigma bonds and 1 pi bond. sp does 2 sigma bonds and 2 pi bonds. Okay, so let's look into that a little more detail. Okay, so we have these 3 types of orbitals, and the sp3 is the 1 s orbital, which is spherical, and 3 of those p orbitals, which are dumbbell shaped, okay? And when we do that, we change the shape so it's a lopsided dumbbell, but we have 4 equal orbitals that can do orbital overlap to give us a bond, okay? And this direct orbital overlap of these hybridized orbitals is what we call a sigma bond. Okay. Now, with the sp, we still have the round s orbital and 2 of the lopsided orbitals, the dumbbell orbitals, giving us a total of 3 lopsided dumbbell orbitals, plus 1 untouched p that's above and below that plane. That p can do what we call a parallel overlap bond, or pi bond, okay? Those other hybridized orbitals, the sp3, the 3 of them that are sp2 hybridized, can only do sigma direct overlap. And so then when we go to the next one where we have the 1s, which is spherical, and the dumbbell shaped, we have a very big lopsided dumbbell, and then we have 2 p orbitals, 1 in the x direction and 1 in the y direction, and the hybrid orbital is going to be in that z direction, okay? That's the most we can spread them out. And the hybridized orbitals will do the direct sigma bonding. The p orbitals must do a parallel or overlap bond, or the pi bond, okay? So Whenever we have just our regular hydrocarbons, we only have sigma bonds. However, once we have alkenes and alkynes, we now have sigma bonds and pi bonds. And that's the key phrase here that we need to look at. Okay, so before we also said in that chart of nomenclature that we had two kinds of hydrocarbons. We have what we call saturated hydrocarbons and unsaturated hydrocarbons. The whole point of unsaturated carbons is that we can actually add hydrogen to the system. We can keep adding hydrogen to the system. Doesn't mean it spontaneously reacts with hydrogen. It just means that we can add hydrogen to the system until all of the carbons are sp3 hybridized. Okay, so that means anything that's not sp3 hybridized is what we call an unsaturated hydrocarbon. So the simplest of this is what we call the alkene. Okay, the alkene is something that has a double bond, a single sigma bond and a single pi overlap bond. Okay, now the general formula of that is this right here, where we have n carbons and 2n hydrogens. Remember, for a saturated hydrocarbon, it's Cn H2n plus 2. Okay, so that plus 2 is those two hydrogens that are being removed to generate that double bond. That's why our new formula does not have that plus 2 at the end, and we have an unsaturated hydrocarbon. Now, when you have an alkyne, you have to take away 2 more hydrogens to get a second pi bond, and the general formula is the Cn and 2n minus 2. Okay, so and of course n is any whole number from 2 up. Okay, can't be 1 because we can't have a double bond between a single carbon. So it's any number 2 and up. Okay, so the generalized structure is what we see here. And again, we have the sigma bonds that are the hybridized bonds that are these right here. And they're giving us that trigonal planar structure. And then we have the second bond where the P is coming up and over, and these P's are overlapping above and below that sigma bond to give us our second bond. Okay. Now, in the example of an alkyne, we have one of these P's is going in one direction, and the other P, actually let me change color, is going in the other axis, okay? Which means these two orbitals that are parallel to each other are the ones that bond together. And the other two P's that are parallel to each other form the second pi bond, okay? Remember, the first bond is that hybridized sigma orbital in the beginning, okay? And so that's why we have what we call those parallel overlap bonds or pi bonds, okay? Questions on that? No hands raised, nothing in the chat, all right. Okay, so this actually has some interesting connotations to it, okay? Because those two p orbitals have to overlap with each other to make this pi bond, it means that we now cannot rotate that bond. If we started to rotate that bond, one P would start to rotate away from the other P, and they no longer overlap. If they no longer overlap, they're not bonded, okay? So that's why if we tried to rotate this bond, the pi, this one that's in this axis, the x-axis here, and this is an axis, if we try to rotate this one out of plane, rotate it 90 degrees, it will break that pi bond. It can no longer overlap. So what that means for us is that when we have something like this, if we have an X group on this side and a Y group on this side, they are fixed in space. You cannot rotate around that double bond because you would have to break the pi bond to do it, okay? And that's gonna lead to some interesting properties that we'll see in a little bit. All right. So because we don't have that free rotation, because it is fixed in space, we now have isomers. And these particular isomers are called stereoisomers, meaning that it's a spatial event. It's basically where they are fixed in space. Okay, so let's look at this one to start with right here. So this is one of the simplest alkenes we can make. It's 4 carbons, and we have a double bond that we can have stereoisomers of. And as we said before, we have the sigma bonds, and then we have that pi bond going up and over, and that pi bond going up and over keeps it from rotating, okay? Which means that this methyl group is always on the same side of this axis. They're on the same side if you cut an axis right down the 2 carbons that make up the double bond, okay? If they're on the same side, we call this the cis isomer. What you can also do is think of it this way. If your groups other than hydrogen make a little C, it's cis, okay? So the other possible isomer when you have 2 things bonded to a double bond is where you have them on opposite sides of that. So if we drew a line between our 2 carbons and our double bond right here, one's on one side and the other's on the other side, okay? And so that's a different isomer because we can't rotate that bond. We can't turn one into the other without breaking that pi bond. If we can't do that without breaking the pi bond, that means it's usually fixed that way in space, and we can actually isolate these 2 things because they're separate, okay? And so because it's separate, we have to have a name for it. We call that the trans isomer, being on opposite sides. Another way to look at that is it looks kind of like a Z with your double bond here. And so it's trans. So that's one way to remember that if you want to, okay? But one of the effects that this has is that because they are spatially different and they can stack differently with those weak forces they have, that means they have different melting points and different boiling points. So not only do we know that these are fixed in space, but we know that we can isolate them and use them separately. Okay, so what's next? Okay, the next thing is, so in the alkene, we had 1 sigma bond and 1 pi bond, and then it was bonded to other things. Okay. In an alkyne, what we end up with is one of our p orbitals being in this, well, let's call it the x-axis here. And then the other p orbital is going to be in the y-axis here. And that our hybrid orbital is in this z-axis here, okay? So that means the one on the z-axis here is this sigma bond, okay? That's the direct bond overlapping between them 2. And then the first pi bond is only the 2 p orbitals in that axis, okay? Those 2 p orbitals in that axis form the first pi bond. The 2 p orbitals in the second axis overlap to form the second pi bond. And so that's how we get the carbon-carbon triple bond. Has to be hybridized in an sp to an sp because you want the sigma bonds to be 180 degrees apart. And then those 2 remaining p orbitals, 1 p orbital from each side in the correct axis overlaps to make 1 pi bond, the other axis to make the So, what makes alkynes so much different from alkenes and alkanes is the hydrogen that's attached to the carbon is starting to become acidic, okay? So in the last chapter that we talked about acids and bases, right? We said that the alkanes are the weakest acid, and then we have the alkenes, and we have like alcohols and water, and then acetic acid, right? So this is the first hydrocarbon that has what we would call an acidic hydrogen, okay? And the reason it has this acidic hydrogen, this hydrogen at the end, we can pull off, is because of that hybridization, okay? Okay. So if we look at this, and we look at an sp3 hybridized orbital, only 25% of that hybridized orbital has spherical character or an S character. But by the time we get to the alkyne, because it's only sp, it's half s and half p, which means it has a 50% s character, and that makes it easier for that carbon-hydrogen sigma bond to be broken, and that makes it so that hydrogen is easier to remove. And so it becomes more acidic. The easier it is to remove that hydrogen, the more acidic it is. Okay. And that is the same thing. The other cool thing about that is because we have that more S character here, when we do remove that hydrogen and leave those electrons there, it can better stabilize that negative charge generator. And so that gives it, the more stable the anion is, the more likely it is to pull off that hydrogen. So again, to rank these in order, sp3 hydrogens are less acidic than sp2 hydrogens, or that's hydrogens bonded to an sp2 carbon or an sp3 carbon, which are less acidic than the hydrogens bonded to an sp hybridized carbon. Okay. So this makes alkynes, if they have a hydrogen, the most acidic of the hydrocarbons. Okay. All right, questions on that? Got to know the names, got to know the hybridization. You got to know how many sigma and pi bonds are in the alkanes, the alkenes, and the alkynes. All right, so that's goal 1. Okay. Now let's move on to goal 2. Okay, so now we have seen that it takes sigma and pi bonds to make alkenes and alkynes, and we know which hybridization is associated with which of those functional groups. Now we get to start naming them, including the isomers, which we started with the cis and the trans. Okay, but that works for when we have 2 substituents. So let's talk about naming them again. And like we said before, these are unsaturated hydrocarbons, and therefore they have at least 1 pi bond in them. Okay. When we talk about alkenes, okay, so we have at least 1 double bond in there, we now have to change the infix and turn it into the en. So it's kind of easy to remember because we call alkenes, and it has the en. Remember, we have the prefix, the infix, and the suffix. When we talked about our nomenclature, the prefix tells us how many carbons are in our carbon chain. The infix tells us whether we have single, double, or triple bonds. And the suffix tells us what other functional groups there might be. In the case of alkanes, the suffix is always E. So the key here is that when we see at least 1 double bond, we have to use en in our name. Okay. So just like naming hydrocarbons, we start with the parent chain to give the longest chain possible with both of the carbons in the double bond. Okay, you must contain both carbons in the double bond in your longest chain. Okay, and you try to give the first carbon of the double bond the lowest number, and then all the other rules apply. Looking at numbering your lowest, alphabetizing your substrates, etc. In the case of cycloalkenes, you number the carbon around the ring starting with the first 2 carbons of the double bond. So if there's no other functional group, we're going to name it from that alkene. So let's do an example or 2. So let's start off with this one up here. This is a nice simple one because all we have is 1 alkene and we have a long straight chain. So that makes it easy for us to start with that one. So we want to start with the idea that it's the longest chain. We have a total of 6 carbons, which gives us hexa. So hexa is what we call, that is the parent chain, that is the prefix, because it tells us the number of carbons, okay? So we're gonna drop the A and add En because we have an alkene in it. And because there are no other functional groups, we're going to add an E at the end. Okay. So now, because because it's at the end, it's sometimes assumed that if you don't put a number on there, it tells you that it's in the number 1 carbon. But the correct answer, best answer would be 1-hexene. So the answer would be 1-hexene. Okay. So let's expand that with a substituent on there. So in this case here, the next case, we have a total of 1, 2, 3, 4, 5, 6, but we have that. So this isn't the longest chain, so this cannot be our parent. So we have to name it for the other chain. And so if we name it for that parent, we have, again, 6 carbons in our longest chain, so we now have hexene. So hexene. And because we have to label from the lowest number in the first 2 carbons here, 1 and 2, that puts our substituent on the number 4 carbon. And so we have with 4-methyl-1-hexene. Okay. So remember to put a dash in between your substituents and the parent. Okay. This right here is the one that has the prefix, the infix, and the suffix in it. These are just substituents attached to it. So let's get a little more complicated, but use the same rules here. Okay. So one might think, oh, well, gosh, we have a much longer chain if I do this right here. We have, you know, it's 7 carbons in a row. But that long chain does not contain both carbons of the double bond. So we can't name it for that. So if we can't name it for that, let's try to find the longest chain with both of the carbons in the double bond. And so that'll give us this unit here. And again, because it's at the end of the chain, we want to start the first carbon at 1 and the second carbon at 2. And that tells us where all our substituents are. Okay. Now that we have our substituents, let's look at what we have. We have an ethyl group here. Ethyl, sorry. And we have a methyl group here. Okay. And so now we get to assign those numbers. And so this is going to be 2-ethyl. And this is going to be 3-methyl. So let's add that all together. Ethyl comes before methyl alphabetically, so we have to put it first. So our answer is 2-methyl-3-methyl-1-pentene for our double bond. Okay. See how we're doing this naming structure there? If you gotta follow the process. Okay, we follow those same rules when we name alkynes. Okay, we again try to get both carbons of the alkyne have to be in the main chain. We find our longest chain. In this case, it would be butyl, but we drop the A and E and add Y and E. The Y and E tells us we have a triple bond. Okay. So our butane becomes butyne, okay? And luckily we have it at the end of the chain, so we have 1 butyne. And if that's 1, that's 2, this is 3, so we only have 1 substituent on there on the 3 carbons, so 3-methyl, 1-butine. Okay? Okay, so that makes some sense here. But what if you have both functionalities in the same chain? Oh, we're not doing that one yet, sorry. Okay, so now they can't all be at the end of the chain, so let's see how to name that alkyne where the alkyne is somewhere in the middle of the chain, okay? So let's start with, let's see. Well, there's only 2 ways, well, you can only ever have the alkyne in the main chain, and these 2 groups are all the same. So it'd be 7 to here, 7 to here. So that means we just have 2 methyl groups as our substituents. So we have a total of 7 carbons. So that'd be heptane. We're going to drop the A and E, add Y, Y and E because we have a triple bond, but it's not at the end. So we need to locate it. So it's 1, 2, 3. If we labeled it from the other side, the first carbon would be 1, 2, 3, 4. So it would be a higher number if we numbered it from this side of the molecule. So we're going to number it from this side of the molecule. And that's going to give us 3 heptyne. And then we have 2 substituents, and both substituents are on the 6th carbon. So we have 6, 6 dash dimethyl 3 heptyne. Now, don't forget the di, tri, tetra does not count for alphabetization. So if we had to alphabetize this, we would alphabetize it based on methyl. Okay, so, okay. Now, because these are used so much industrially, they tend to have common names, okay? And so a few of these common names you'll see out in the world, and so I wanted to expose you to them. And these 3 common names in particular probably are something you should remember at least for the next exam. So if we were to name this IUPAC, we have 2 carbons, so that would be ethane. But we have a double bond, so that makes it ethene is the IUPAC name, okay? However, industrially, we're naming it as the ethyl group. So it's ethyl, but it's an alkene, so it's ethylene, okay? So if we move up to 3 carbons here, this would be the propane, drop the A and add E-N-E, and we end up with the IUPAC name of propene, okay? And, let's see, but the industrial name is like before. We have 3 carbons, so that's the propyl group. But it's an alkene, so we're going to put ene at the end. Okay. And this one right here is, if we look at it, it's propene, but it has a methyl on this number 2 carbon. So we're going to 2-methyl propene, but it's called isobutylene. Okay, and the iso means like isomer of it. So it's isobutylene, 4 carbons total. So that makes it butyl. Iso meaning it's an isomer, and ene meaning it is a double bond. Okay. So
I have a quick question.
Yes.
I just want to make sure, you were saying that we need to memorize these. Are you saying the common name or the IUPAC name?
You should be able to derive the common name just using the rules. But these 3 names are ones you might want to just memorize if you don't get the naming process.
Okay, thank you.
But you should be able to do the IUPAC name no matter what. And the IUPAC name is always right.
Is the test going to be multiple choice?
Yes. Okay.
Thank you.
All right. So with the alkynes, we name them that same way. And so I have actually already named these already. So the only thing that's different in the alkynes is we drop that A-N-E and we make sure we have the Y-N. The Y-N is signifying that triple bond. Okay. So now we have a couple different types of isomers possible when we look at alkenes. We don't have isomers when we have alkynes because it's 180 degrees, so we don't have that cis-trans isomerization. We only have cis-trans isomerization in alkenes. So that's one thing to look for. We don't have it in alkanes either. We have different nomenclature for that. So in the case of 2 groups that are if we draw a line, we got to draw a line through the 2 carbons of the double bond. And now we assess whether the 2 different groups attached to the alkene are on the same side of that line or the opposite sides of that line. If they're on the same sides of this line, we're going to call that cis. Okay, and so that's the cis isomer of the material. Okay, now if they're on opposite sides, we're going to call that the trans right here. Now notice in this case here, we're also naming it with the longest chain. We have 1, 2, 3, 4, 5, 6 carbons total. The first carbon of the double bond is on the number 3. So we have trans 3-3-hexene as its double bond. In this case right here, we actually have 2 methyl groups at the end. So we actually can call it, there's going to be a total of 5 carbons in our longest chain, giving us pentene. And the first carbon is on the 2 position and the 3 position for the alkene. So that's where we get the 2-pentene. And then we have a methyl group here and a methyl group there. So that's how we have the 3,4 dimethyl. Now notice, both of these big groups are on the same side of that double bond, making it the cis isomer.
Why is that top CH3 not highlighted red?
Okay, because that takes us to our next rule, actually.
Okay.
Which is the E and C naming system. Okay, so in this one right here, why is that methyl group the higher priority? Why is that methyl group not highlighted, right? That's your question. And that's because in this particular case, it's simple enough that we can say that on this side, this is the bigger group. Where's my cursor there? On this side, this is the bigger group compared with these two. And this is the bigger group compared to this side. Okay, so that might be a little ambiguous. So that's why we came up with the EZ method, okay? And that clears up any ambiguity, okay? So in E and Z, we can use things other than just hydrogens attached to our double bond, okay? And so what we're looking for is we're looking at each side of the double bond, but we have to look at the double bond 2 different ways. So the first way we have to think of the double bond is we have to think of splitting this double bond, and so we have side A and side B, okay? And so what we do to assign E and Z is we find out which is the highest priority, or what's the highest priority or the largest atomic number on side A first. And then we assign what's the highest priority on side B. And then we do the exact same thing we did with cis and trans. In fact, we draw a line through our double bond, and we see, are they on the same sides of that axis with the double bond, or on the opposite sides of the axis, okay? So in that case, if this was the higher priority, and this was the higher priority, that puts them both on the same side, which makes them, the German word for together is zusammen, okay? The other way to remember that is Z is for Z groups on Z same side, okay? So it's kind of like cis, but it works for things that have more than just small groups like hydrogen here. Okay. The opposite of that is we do the exact same thing. We first split it into A and B. We look for what's higher priority on the A side and assign that. We then look what's higher priority on the B side and we assign that. And we draw that line through our double bond and we look to see where A and B are. If A and B are on opposite sides of that line drawn through the double bond, that makes them opposite, or the German word entgegen, or the E function, okay? So it's zusammen and entgegen, but if Z and E are the numbers we need to write. Okay. So the key is to do it stepwise. Divide your molecule through the double bond and assign A and then assign B, and then look at whether A and B are on the same side going through both carbons of the double bond or not. If they're on the same side, it's Z. If they're on opposite sides, it's E. Okay. So how do we know what priority is? Okay. So this says higher priority and lower priority. Okay. Before, when we just had carbon and hydrogen, well, carbon was more important because that helps name the compound. So how do we assign priority? Okay, priority is based on atomic number, not atomic weight. There's a couple that switch. So atomic number. Okay, so as you move over on the periodic table and go down, that's how you increase it. So that being said, that means hydrogen's always the lowest priority because it's atomic number 1. Carbon is atomic number 6, and that's one of the ones we'll see where we have carbons coming off and on. And then we move nitrogen, oxygen, and then fluorine is actually in here at 9. And then as the atomic number goes up, the priority goes up. Okay. So if you had a hydrogen, a methyl on one side, the methyl has higher priority. If you had a chlorine and an iodine on the other side, the iodine had the higher priority. So it's atomic number first. Okay. If that doesn't definitely tell you what is the highest priority, you have to look to the next atom over. So let's say you had a carbon on one side and a carbon on the other side, and on one of them you had a methyl group, and one you had an ethyl group, okay? So now we're looking at one bond over. One bond over, we have an atomic number of 1. One bond over, we have carbon, atomic number 6. That makes this higher priority than that because it has a higher atomic number attached to it. Yes, there's a question.
So I just wanted to clarify, the EZ is for assigning priority on a single carbon atom, while the Cis-Trans is assigning priority or what side they are across the double bond.
Not exactly. Priority is assigned to each of the groups attached to our double bond. Okay. So we're just assigning, these priority rules are all about assigning where they are on the double bond. So for example, for what we could have a priority of 1, which would be hydrogen, a priority of 6 here, and we could have a priority of 6 here and a priority of 12 here if we had a different atom there. Okay, so this being the higher priority on this side and this being the higher priority on that side makes it into this same side of the double bond, so it's like cis, but it works for things other than hydrogen. Usually we only assign cis and trans when we have 2 groups attached to the double bond. If you have more than 2 groups attached to the double bond, we use the E and Z. Does that answer your question?
Yes, thank you.
So, and then, but the E and Z are similar to cis and trans, but we worry about the atomic numbers, not whether or not it's a hydrogen or a carbon. Yes, I have hand raised.
Yes, sir. So essentially, like, we're not going to have a problem where we're going to have, obviously we'll have to know the difference between the two, but we're not going to have a problem where it's still going to be super hard to differentiate which one's which, right?
It should not be, and we're going to do a few examples.
Yes, sir. Okay, I appreciate it.
So, but it should be fairly straightforward to identify higher priority. Okay. So, for example, in the case of if we just had the single atoms attached, we could assign just by atomic number. However, if you have a carbon on one side and a carbon on the other side, what is attached to those becomes important. So in the case of, like I was showing here, if we had only a hydrogen attached to one carbon and a carbon attached to that carbon, the carbon is higher atomic number and it takes precedence. Now notice that if we put a nitrogen there, nitrogen has a higher atomic number than carbon, it's higher priority. Again, if there's an oxygen attached to the carbon one over or the higher one over. So if you cannot tell it from the first rule, which is just what's attached, you have to go to the second rule, what's attached to those 2 different things that are of equal priority. Okay, so the third rule associated with this is how do you deal with double bonds, okay? Now, when you have a double bond there, that means you had a carbon attached to your double bond, okay? And that carbon now has a hydrogen on it, but it's attached to another carbon. So what we're gonna do is we're gonna count each of those bonds and which atom is attached to each of those bonds. So in the case of an alkene here, that means that carbon is attached to one hydrogen, one carbon, and then the second carbon through the pi bond, okay? So that means that this right here is actually attached to one carbon through the first bond and one carbon through the second bond, and that helps it assign priority. The same works for if you have a double bond to an oxygen here. This is treated as if the carbon was attached to an oxygen right here in our first bond, but our carbon is also attached to this oxygen and another carbon by the second bond. So that would make its high priority a oxygen-oxygen, so two oxygens to establish priority. Now, whether or not the thing next to it is higher or lower. So let's try to use these rules, these three rules, and do a few examples. Okay. Let's do the examples first. Oh, I don't have the examples. Oh, darn. All right, let's actually switch over to something and do examples because it's important. Go to open blank. All right. Okay, so here's what we're going to do. We're going to do one example and we're going to show what we're going to do. So I'm going to draw okay. So first rule is we have more than two things on our double bond, so we have to use E and Z. Okay. Second rule, divide the double bond this way and assign priority to A side and then assign priority to B side. So let's assign priority to B side, okay? The atomic number for chlorine, this is atomic number 6 for carbon, and this is higher. It's 14? No, it can't be 14. 17. So it's atomic number 17. So that means chlorine is the higher priority one on that side of the double bond. So what we're going to do is we're going to go ahead and just circle chlorine as our highest priority on this side of the double bond. Right here. Okay, now we go and assign priority on the B side. And on the B side here, we have carbon right here. Okay, and then really this is a carbon attached to an oxygen, a carbon attached to an oxygen attached to a carbon, and a hydrogen. But this is number 6, atomic number 6. Okay. Oxygen is atomic number 8. Atomic number 8 is higher than 6, therefore this gets priority. So we know that those two are A and B priorities. Now let's draw a line through both of the carbons of the double bond. And we see that they are both on the same side of that, meaning that it is a Z configuration. Z, Zane, Zi. Okay. Let's do one more example, just to make sure we have our priority thing down. And the example we're going to use is let's use This one. All right. So we're going to go through the same rules. We're going to divide it here, and we're going to look at one side first and the other side here. So here we have 6. Here we have 6 plus a 6. So that means this is our highest priority group. So we're going to circle that. And if we look at the atomic number on the other side here, this is atomic number 8. This is atomic number 7. That makes this the highest priority on this side. So we're going to circle that. And now we're going to draw our line through the middle of the double bond. One is on one side of the double bond. One is on the other side of the double bond. That is opposite. Therefore, this is the E configuration of this alkene. Okay, does that make sense?
Could you show like an example versus cis and trans, like what a picture would look like for cis and trans?
Okay, let's do, that's a great idea. Okay, so the difference in the idea about cis and trans is if you have more than 2 groups on your alkene, you have to worry about cis and trans. I mean, if you only have 2 groups, you assign it cis and trans. If you have more than 2 groups, you assign it E and Z. So in the case here, we have, let's draw that right there, okay. This is neither cis nor trans because the other groups here, when we draw them on there, are hydrogens, and this is a methyl group. So that means an alkene at the end of a chain is not cis, is not trans, is not E, and is not Z. Okay. So if we put any 2 groups on a double bond, now we have to assess on whether they're on the same side of that axis or not. So we're going to draw a line through our double bond here. And we have one group is on this side and one group is on that side. So that gives us our trans isomer. Okay.
Thank you.
And then when we have 2 groups like OH, H, H, CH3, this would give us our cis isomer. Okay?
Thank you.
I still have a little bit of confusion with the way that it's drawn out.
Okay.
So like with whenever, can you go back to like the last page or no?
The examples or the page?
So with oh, not that one.
The one in the chapter note?
Example.
The example I was
Yeah, the example you're doing.
on blank.
So when you draw it out, if you don't have like the Cl or the OH, does that just mean it's like a methyl group?
Correct. Remember, when we do skeletal structures, if any line indicates a sigma bond and any end signifies a C with H's on it,
Okay.
unless it's explicitly written out as an element, we assume
Okay.
this is carbons and hydrogen.
Okay. Thank you.
Okay, so we have cancel. We have a couple slides left. Okay, so let's talk about how we can see alkenes in rings, okay? Now, if you have a small ring, for example, this cyclopentene right here, you do not have the possibility for cis-trans isomerization. There's not enough bond length to allow it to get to that trans configuration. So all the small, the cyclopentene, cyclohexane, and the cyclopentene and hexene can only make the cis isomer, okay? And it's very difficult to make, you cannot make it with the heptane either here, okay? Oh, we didn't, that's not the heptane, that's the octane, okay? The first time you can have cis-trans isomerization in a cyclic compound is when you have octene. So you have to have 8 carbons in a chain, and when you do that, you can have cis-trans isomerization because if you draw a line on through your double bond here, this side, this carbon's on that side and this carbon's on that side. So this actually is the trans octene configuration. And this would be the equivalent, which is the cis octene, where they're both on the same side of this double bond. So we can even draw the double bond here. We have one on one side and one on the other, giving us our trans configuration. So it's very unusual in rings to have anything other than cis unless they're big. Okay, so that takes us to the possibility of, well, we have the possibility of having more than one double bond on a main chain. And the way we take care of that is we say, okay, we have multiple double bonds, and we're going to call them, if we only have two, we're going to call them a diene, 2 alkenes, a triene, 3 alkenes, and we can have more and more and more. So when we do that, we have to assign where each of those alkenes begin. So in the case of just assigning the name to this structure here, we have a total of 7 carbons, giving us hepta, okay? We have 2 double bonds, and the first double bond is on carbon 2, the second bond is on carbon 4. So that gives us 2, 4, hepta, diene, okay? Because we have 2 alkenes in 7 carbons, and we've assigned it. First one is on 2 and the second one is on 4. But now, because each of those double bonds has at least 2 things attached to it, we have to assign cis and trans. So when we assign cis and trans, we draw our line here. And the 1 and the 4 are on the opposite side. So that makes this the trans bond. And then we have to do the other one too. And if we draw our line here, the 3 and the 6 are on opposite sides. And that gives us our trans isomer. Okay. So what would happen if we break the bond between 4 and 5 and flip it up so it's not the trans isomer anymore? Well, we get the other isomer. And so if we look at this one right here, our 1 and 4 are still opposite each other, so this is still trans. But if we draw our line here, the 3 and the 6 are on the same side of that double bond. So we have to assign it as cis. Okay. And we put them in the exact same order that we would put the numbers on it. So this trans is associated with this 2. This trans is associated with this 4, which means that trans is associated with the 2, and this cis is associated with the number 4 carbon. Okay, so we can actually draw a total of 4 isomers possible here, and those are actually 4 different compounds. Okay. Even though they have the same molecular structure, they are isomers of each other because they have different cis and trans conformations. Okay, questions on cis and trans, E and Z. So look at it this way: if you have 2 things on there, you can name it cis and trans. If you have 1 thing on there, it's the end of a chain. You don't have to identify the isomer. If you have 3 or more, use E and Z.
Could there be E and Z on cyclo?
It is possible for bigger cyclos, like the cyclooctene can have an E and Z. But again, it goes to if you have a substituent on your ring. So for example, we would have to put like a methyl group or something hanging off this double bond to have to worry about E and Z.
Okay.
So it doesn't matter what's in or not, it's 2 or more substituents on your double bond. Okay. Good question. All right, that brings us to our last goal for this chapter. And our last goal about this chapter is physical properties and the different kinds of intramolecular bonding that it can do. Okay. Okay, because these are unsaturated hydrocarbons and they don't have any other functionality to them, they bond similarly to what we see in regular saturated hydrocarbons. They don't have a very strong bonding associated with them. Okay. So And because of the fact we've changed the hybridization from the sp3 hybridization, which is the tetrahedral at 109.5 degrees, we've now changed it such that because we now have sp3 hybridized, we're now trigonal planar, and we have that 120-degree bond angle between the different substituents, okay? So that gives us this flat plane between these three atoms and a flat plane between those three atoms, making the molecule completely flat, okay? So even when we have a substituent there, this molecule is still flat on this plane right here. So now, if all things are created equal, it would be 120 degrees. But the fact that the hydrogens are smaller than the carbon, it makes the carbon is a little bit bigger, and therefore it pulls that angle out just a bit from 120 to almost 122 degrees. And the same thing happens when we have this methyl group is now pushing against it too. They're pushing each other apart, and the angle gets slightly larger, but it's still targeting that approximate 120-degree angle. Okay, with the alkyne, you don't have to worry about it. It's going to be linear no matter what you do. Okay, that being said, the carbon-carbon double bond is not a polar bond, okay? The carbon-carbon single bond is not a polar bond. Both atoms have the same electronegativity. Even though we're making a double bond between them, we still haven't changed the polarity. This is still a non-polar bond. What that means is the only attractive force we have between two molecules are the dispersion forces, or London forces. So it's that induced dipole, which means that the longer they are, the straighter they are, the more surface area they have, the more it will raise the bond. So, you know, and the boiling point rises because of number of carbons first, and then forces interacting on it second. So, that being said, alkenes, because they're a little more compact than the saturated hydrocarbons, because we have that double bond, they're actually slightly higher in density than that of alkenes, okay? They tend to be, most of them tend to be liquids or solids at room temperatures, and they are just below water, okay? Hydrocarbons are like 0.45, alkenes are just a little bit. But because they don't hydrogen bond, they are insoluble in water as well. So they tend to only dissolve in other hydrocarbons and not very polar organic solids. Okay. So the big thing we're going to play with, especially with the alkynes, is the idea that we can remove that proton. Okay, that proton at the end of an acetylene, if we have a terminal alkyne, that means we have a hydrogen at the end. Because that hydrogen is acidic, we can pull it off with a strong base. Okay, so in this case here, we're actually looking at the pKa of this acetylene here. The pKa of acetylene is 25. It's the strongest of the hydrocarbons. And we use a very strong base. Notice that this is a nitrogen, but it has a negative charge on it, so that makes it a really strong base. Once we pull that proton off, we end up with ammonia as our new conjugate acid, and our conjugate acid has the pKa of 38. That is higher than 25, making it the weaker acid, which shifts the equilibrium to this side, which means that we can form the acetylide ion. Once we form this anion here, we can use this anion to attack other substrates and make new carbon-carbon bonds. Okay. Now, because of the base strength is so important, we have to make sure we don't do this reaction in the presence of alcohols or water. We have to do it in something that doesn't have an acidic hydrogen or something that will make something that's a stronger acid. So in the case of the acetylene, we can actually use hydroxide to pull that off, okay? Because once we pull the hydroxide off, we have water has the pKa of around 15, and that's stronger acid than this, and therefore we cannot deprotonate acetylene with hydroxide. we always go to that amide. That's typically that nitrogen with a negative charge on it to make it get deprotonated. Okay, so it's good to keep these, this kind of series in your head as not the absolute values, but the relative series is that our alkane is sp3 hybridized and is very weak acid. It's the weakest acid we probably do. Our alkene is sp2 hybridized. It's a little more acidic, but it's still not as acidic as water. Our alkyne is sp hybridized. And it's the most acidic of the hydrocarbons at 25. But it's still not acidic enough to be deprotonated by hydroxide. We have to use something like sodium. Okay. Questions on that? Oh, sorry, I should close it. So that's the properties associated with alkenes and alkynes. And the idea that we have to have hybridization and we have to have at least one pi bond to make an alkene or an alkyne is the driving force. Now, that pi bond also leads to its reactivity. So, are there any questions about just the concept of alkenes and alkynes? Because I want to go to the reactions of alkenes and alkynes. I want to show you that that pi bond is the reactive species in these things. The last slide I was on is chapter 4, goal 3. Last slide. This one right here. So the key is that relative scale. The alkanes are non-acidic at all. The alkynes are the most acidic of our hydrocarbons. All right, there we go. Everybody done writing that down? Okay. All right, so now we're starting to get into chemistry. Okay, we've explained how the molecules are hooking together, how the atoms are hooking together to form these molecules, and now we have these types of bonds that we can actually do reactions on. And that's where we're going to focus our goals for chapter 5. So the first goal of chapter 5 is to talk about what we call reaction mechanisms, okay? And then we're going to go on to carbocations and other reactions. But the key thing here is that a reaction mechanism is the step-by-step description of what occurs in the reaction, okay? And so we're basically looking at what bonds are breaking or being formed, what is the order of the things happening, and what is the relative rate of these different reactions happening. We actually have a major role of the solvent. The solvent can speed things up or slow things down. We also have what the role of the catalyst will be. Sometimes things are acid catalyzed or base catalyzed. We need to know which one it is because that tells us something about it. The other thing a reaction mechanism tells us is, are we getting energy out of the reaction or are we putting energy into the reaction? Okay, sorry about the bad pun, but it's really. So the first thing we need to think about when we talk about reaction mechanisms is we want to talk about what we call an energy diagram, okay? So in an energy diagram, we have a few things we need to pay attention to. First of all, in this right here, we have a relative scale of energy, okay? That means that, you know, if something's down here, it has less energy than something up here, okay? That's all it means, okay? The other axis right here is what we call the reaction coordinate. What that basically is what's happening during that specific time for that specific molecule, okay? So it's not an actual place in space, it's a place in time, okay? So at the beginning of our reaction here, we're gonna start with our starting materials, okay? So we're gonna add two materials together. They're gonna have a certain amount of energy associated with them, just it's stored in them as the potential energy of those chemicals. Whether they be multiple bonds or, you know, a polar bond or something, they have a certain amount of energy. Okay, and they will just sit there and nothing will happen unless there's enough energy added to the reaction to make them react. Okay, so that's what we were talking about when we're starting to climb up this energy barrier. It takes energy to get this molecule near this molecule in a position to where it can do something. Okay, and so we call this, you know, our energy barrier to get to that point in the reaction dynamics where one bond is breaking and one new bond is being formed. Okay, so the transition state is this mythical, you know, infinitesimal little time and space where one bond is being formed and one bond is being broken. And it's our transition state because it doesn't actually make an isolatable compound. Okay? It's not an intermediate, it's a transition state. It's where one molecule is coming in and the other molecule is leaving. Now, the energy it takes to do that is what we call the activation energy. Okay? If you don't have that much energy in the reaction by light or heat or something, you just roll back down the hill and you stay starting materials. Okay? If you do have enough energy to get to this transition state, then you have an opportunity to go down to products, or you can even roll back down to starting materials. Okay? If you roll back down to product right here, you now have a new chemical bond. That new chemical bond has a different amount of energy than it did when you had the other material starting there. That energy can be greater than the starting materials or less than the starting materials. And so that difference in energy from here to here is what we call the heat of reaction. Okay? So that's how to read an energy graph. It's just telling you what's happening when and the relative energy associated with it. Okay. So, not all energy diagrams just have one point. So, I said in that transition state, it's this time, this point in space where one molecule is making a bond and something is breaking a bond, okay? But you can't isolate that transition state. However, if you break a bond and make something that will then again react to do something else, that you can isolate that. We call that an intermediate. So in that case, in this energy diagram, we actually have two different reactions happening before we get to products, okay? And so we call that a two-step reaction. So we start with our energy, we start with our two compounds here, and we have to add a significant amount of energy to hit our first transition state. Once we hit our first transition state, we get to some stable intermediate, meaning that it stops there, it can be isolated. Okay, however, that intermediate is reactive, and therefore we have to go up a second activation energy. Notice this second activation is usually less than the first one. And then when it cascades down, it gives us final products. So the key step here is that we actually have these two different active energies tell us we're actually forming an intermediate. Without those two humps, you do not form an intermediate. It's just a one-step reaction. Now the key step here is, where are the products? In this case here, the products are below the energy of the starting material, okay? That means the starting material had more energy than the products, okay? So what happened to that energy? That energy is released as heat, okay? When we release energy as a heat, we call that exothermic, giving out heat. So the reaction heats itself up as it goes. So anytime you have a product that is lower in energy than the starting materials, you have an exothermic reaction. All right, so let's talk about each of those individual things. The transition state is that imaginary partial bond forming, partial bond breaking. The activation energy is the energy it takes to make that imaginary bond forming and breaking happen. If you have a very big hump, the reaction tends to run very slow because it takes a lot of time to get that many molecules to react at that high enough energy. If we have a very small hump, that reaction tends to go fast. If the difference in energy from your starting materials and your products is less, is if your products are below your starting materials, you give off heat, and it's called exothermic. If your product is above your starting materials, then it takes heat. It took energy into those new bonds. It's storing more energy, and therefore heat is absorbed. Okay? Now, if you have two humps, you have an opportunity for that reaction intermediate. It's typically highly reactive, but you can isolate it. And we have what we call the rate determining step. That means that this is the one step that slows everything down, and it's always the slowest step in a multi-step reaction. So in that first diagram I showed you only had one hump. That is the rate determining step. In the second one I showed you two humps. The one with the higher activation energy was the rate determining step. Okay. So I want to actually say mechanism patterns next. So does anybody have any questions about the idea of an energy diagram? It basically is telling us a lot of information about what's happening in the reaction.
For testing wise,
Yes.
will you give us like a diagram like this and ask questions about like labeling or like specific questions?
So, for example, I could say, you know, this is A, this is B, this is C, this is D, this is E, right here. And I could say, you know, what would D be called in an energy diagram? What would C be called in an energy diagram? And you would have to know that, oh, that's the top of the hill, that's the transition step. That's the part in between two activation energies, that must be the intermediate. You must know, you know, just the different parts of the energy diagram. I believe they're all labeled on this one right here.
Thank you.
Transition state, intermediate. Notice the top here, this is your first step and your second step, so it's a two-step reaction. If the products were up here, that'd be an endothermic reaction. If the products are down here, it's an exothermic reaction. So those different terms are the important in identifying and understanding an energy diagram. Okay? Okay, we're coming up on 1:50 now. I have time for a couple more questions. And I want to save the different steps because there's 5 things that can happen in a reaction mechanism. I want you to see them all on the same day. Okay, so we'll pick up on that on Monday. All right, any questions?
I missed the beginning with all your notifications for the week. So chapter 3 is due Monday the 14th.
Yes.
And then when will chapter 4 be due?
Let's see, we should be, let me look at my schedule here. There is a schedule on,
the one on Canvas says chapter 3 and 4 was supposed to be due on Friday, but I don't think it's been updated.
Okay, that has not been updated, yeah. Let's see, 3 and 4 were supposed to be on Friday, but we just finished 4 today. So 4 is due on Friday. Yeah, 3 and 4 should still be due on Friday the 9th, the 11th. Because we just finished 3 and 4 today.
Because Top Hat says chapter 3 isn't due till the 14th.
Oh, is that true? Did I change that?
And there's no chapter 4 homework on Top Hat.
Okay, I see. All right. Yeah, okay, so count on the 14th for both. So that's 14 for 4 and 15 for, let me assign the top half. Yeah, so 13 is on 4. Let's 610 points. Assign the homework now until okay, so let's space that out and give you till the 16th to assign that. And I will assign the chapter 5 homework to be the following Friday. There we go, thank you. That would be the 18th. 59 p.m. There you go. Those are all assigned correctly now. I'll double check on Canvas and see when those are assigned as well.
Thank you.
All right, let's see. And it's due at the, I need to change that. All right, thank you very much,
Professor.
Yeah, that was great. And I will see you on Monday. Edit. And save. All right. Perfect. 3 is due September 14th. Let me make sure it's on the right time. 59 p.m. Yes, excellent. Thank you so much. All right, look for this video in just a couple hours.